All right, so let's talk about the 10 questions, actually 9 questions. You have done some of this work and you're probably gonna guess this, right? What is the shape of the cell, of the cells? Obviously it's a square in the graph paper or in the graph paper type of background. What are the two possible states of the cell? Well, the cell is still either alive or dead. So these are all the questions you have to answer. If you answer these questions wrong and you lost points, you have to fix them. You can get your points back. Number 3, how many neighboring cells each cell interacts with? Well, there should be a total of 8 of them, right? So if we look at one of these locations right here, let's take a look at this one. You have above, below, left, right, and left, and then you have the diagonal ones. In total, is 8 of them. Where's my graph paper again? Let's use my graph paper. Hold on a minute. I don't think I need it anymore, but let's just do that anyway. No, I don't think I need it. What's the next thing? So I already told you question number 4 also. What are the rules at each step in time? You need to put the 4 rules that are very clearly identified right here, right? Here they are. So you have to specify clearly the fact that how the cell that's alive can continue to the next, cannot continue to the next generation when it's fewer than 2 live cells are the neighbors. Then how does it go to the next generation when it has 2 or 3 live neighbors? When does it die? Then is when it's overpopulated, more than 3. And more than 3 doesn't mean just 4. Make sure and understand that you can have up to 8 neighbors. Okay, so somebody answered with a 4, and that's not the correct answer. And then if a cell is dead, it can come alive if you have it has exactly 3 live neighbors. Okay, so that is that question. Let's go back to that was number 5. So those rules have to be there clearly specified. So what are the initial patterns? The initial patterns are what they call the seeds, and there are 3 types of seeds, and that comes up as what are the seeds. Then what is referred to it by a tick? Some of you answer with it's a unit of time or the period of time. I think the correct answer based on what is discussed in that Wikipedia page is the generation, right? So the next generation is the next tick. The next tick is the next generation. So use that language besides saying the unit of time, which is okay, but let's be more appropriate according to what the definition is in the write-up. But let's go back. Yeah. So the next one is what are the criteria that must be met for the proper emulation to be successful. So this is the number 8 is actually the key to the answer of your algorithm. How you're going to write your algorithm in terms of you have the rules, but how do you implement those rules? And when I show you before how to use the graph paper, I show you that you have to have you could actually have like the previous and the next, or the current, previous and current, or you can have the current and next. I mean, you could have, but in the end, you need to have two boards, if you want to call them. Um, so, because things have to happen, and if you go down here, they have to happen simultaneously. Simultaneously means that all these things will happen at the same time. If you remove one of the cells to calculate what will be the state of the surrounding cells, then what's going to happen is that you are changing the original state of your board as you update it. And that will not be good. So you need to have two boards. And when I say you need to have two boards, what comes to your mind? How do you represent a board? And so then from there is how would you represent two boards? Make that clear on 8. If you didn't, do it now. What are the different type of patterns that occur in the game of life? So some of you gave me actually the names like beehive, beacon, glider, but that's not really the type of patterns. They belong to each of the patterns. And so the beehive represents one of the examples for the still life pattern. The beacon is an example for the oscillating seed, oscillating pattern seed, right? And then the glider represents a spaceship pattern. That's another seed also. Meaning from here, different things will take place. And in particular, this one returns to the same cycle. All of them return to the same cycle. They don't turn into something different. There are other seeds in which that will happen. I think I answered all the questions. Since I answered all the questions, I just want to tell you what it is next. So to be able to implement this properly, you have to kind of integrate all these things together. In the bouncing ball, you learn animation. And you know how animation works. You know that you need to have the function show and the pause, and you have to have that to draw everything you need to have at each individual refreshing of the screen, right? The checkerboard shows you how to actually use blocks, and then the graph paper gives you the straight lines in which you can see things going through, like in here. I think it's important to have that graph paper look in the background. And then you have the blocks from the checkers, and then the random block was the one that you actually develop somewhere there. So technically, what it happens is that the game of life turns out to be pretty much a much more sophisticated random block. So you were able to have the random block working. Now it's random, right? Now you have to turn it into following the rules, the 4 rules of the game of life. Again, these are the ones. And so now that random block that you created with graph paper and with the checkerboard code and with the animation from Bouncy Ball, now put into that program the rules of this behavior of the blocks. There. And Minesweeper, now we should come into Minesweeper, in terms of the neighboring cells for each of them. And again, one more time, the fact that you have to have 2 boards. So when you make changes to one of the cells, does not affect the behavior of determining what the next cell will be in the next generation. That's the trick.